going after the hardest target in all of physics. Not planets, not stars, not even galaxies.
No.
We were going straight to the beginning. We're looking for evidence from the very first, well, the first incomprehensibly tiny fraction of a second of existence.
And that's the right way to frame it, a hunt. We are investigators at the oldest crime scene imaginable, and we're looking for a fossil.
A fossil?
But this isn't a bone buried in the dirt. This is a scar. A scar on the sky.
A scar on the sky. I love that. What exactly are we calling this 13.8 billion-year-old fossil?
So the technical term is primordial gravitational waves, or PGWs.
PGWs?
Right. And you should really think of them as just that ripples in space-time itself that were, generated when the universe was unimaginable young.
And they're still here.
They're still here. They are the universe's first heartbeat, still vibrating through us, through our instruments, everything.
The sheer audacity of this entire mission, it's what's so compelling. If we can correctly read this scar, if we can measure this, this faint twist it left behind.
Then you're reading the diary of the universe's first moment.
An era that should be completely sealed off from us.
It connects you, the person listening, directly to the physics of creation. It's not just abstract math anymore. It becomes a physical imprint. We're using the largest thing we can see, the whole universe, to probe the smallest, highest energy moment in all of history. We're going back to the first 10 to the minus 36 seconds.
So to get there, to understand that fossil, we have to look at the catastrophic event that created it. We have to talk about inflation. And this wasn't just a gentle expansion. This was violence. This was space ripping itself apart faster than the speed of light.
Violence is absolutely the right word. We are talking about a period that starts around 10 to the minus 36 seconds and is probably over by 10 to the minus 32 seconds.
I can't even wrap my head around that time scale.
Nobody can. But in that sliver of time, the universe can bigger by a factor of at least 10 to the 26, maybe much, much more.
Driven by what?
A hypothetical field. We call it the inflaton. But the why it happened is almost secondary to the sheer, unbelievable chaos of it.
And cosmologists needed this event, right? This isn't just a cool story. The standard Big Bang model had some serious holes in it.
It did. Inflation wasn't just invented to sound dramatic, it was necessary. It solves two huge problems with the old model, the horizon problem and the flatness problem.
Okay, let's slow down and take those one at a time. The horizon problem. What is it, and how does ripping space apart fix it?
The horizon problem is, it's a question of temperature. You look at one side of the sky and you look at the complete opposite side. They're exactly the same temperature.
Down to a tiny fraction of a
It's
degree.
1 part in 100,000. In the old Big Bang model, those 2 points should never have been in causal contact. Light never had time to travel between them to even out the temperature. They should look totally different.
Like trying to mix 2 cups of coffee that are on opposite sides of a country, they're not going to end up the same temperature.
Exactly. Inflation solves this. It says that before the Big Rip, the whole observable universe was incredibly tiny. Small enough for everything to be in close contact, to mix, to reach the exact same temperature.
A perfectly smooth, tiny patch.
And then inflation takes that smooth, equilibrated patch and just stretches it to cosmological size, pushing those now uniform regions way beyond each other's horizons.
Okay, that makes sense. And the second one, the flatness problem.
The flatness problem is just as weird. General relativity allows for the universe to be curved. It could be like a sphere or like a saddle, but we measure it and it's flat, perfectly geometrically flat.
And that's unlikely.
It's astronomically unlikely. Any tiny bit of curvature at the beginning would have been magnified billions of times over as the universe expanded. For it to be this flat now, it had to start out flat to an absurd degree. 1 part in 10 to the 50.
Which seems impossible.
Unless you have inflation. Inflation takes whatever initial curvature you had and stretches it out so much that on our local scale, it just looks perfectly flat. It's like an ant on the surface of a basketball. To the ant, its world is flat.
So inflation is this required, violent event. And the crucial part, the thing that actually makes our fossil, is this concept of the frozen vacuum. That sounds like something out of science fiction.
It does, but it's pure quantum field theory. The key is to understand that the vacuum is never really empty. It's not nothingness.
It's boiling with activity.
Constantly. Quantum fluctuations. Little pairs of virtual particles, a particle and an antiparticle, pop into existence out of nothing, and then, poof, they annihilate each other almost instantly.
They borrow energy from the vacuum and have to pay it back fast.
Exactly. In our normal, calm space, this happens on microscopic scales. It's a constant subatomic jitter.
But during inflation, the rules are completely different.
Because space itself is expanding faster than light. And this superluminal expansion creates an escape route. When one of these quantum fluctuations pops into existence,
It gets caught in the current.
it gets yanked, pulled apart. Before the particle pair can find each other and annihilate, the sheer violence of the expansion stretches its wavelength from a tiny quantum jitter into a macroscopic gravitational wave.
A wave the size of the observable universe.
You've essentially captured a flash of lightning and stretched it until it covers the entire sky. That original quantum state is literally frozen into the geometry of the universe. It's locked in, like a ripple flash frozen in a pond.
And these frozen ripples are the seeds for everything.
Everything we see today. But they come in two fundamentally different flavors, and this distinction is absolutely critical.
Okay, so we have the boring ones and the exciting ones.
Well, they're both vital, but yes. The first type are the scalar perturbations. These are fluctuations in the energy density of that inflaton field. Think of it as the primordial soup being mostly smooth, but with tiny pockets that are just a little bit denser or a little less dense.
The lumps in the gravy, so to speak.
A very good analogy. Over billions of years, gravity gets to work on those lumps. The slightly denser regions pull in more matter, they get even denser, and eventually they collapse to form.
Galaxies, clusters, the entire cosmic web.
All of it. These scalar fluctuations are the reason we have any structure at all. They're the source of the hot and cold spots you see in maps of the cosmic microwave background. They're the background noise.
But they're not the fossil itself. The true prize, the direct evidence of that catastrophic inflationary event, is the second type.
The tensor perturbations. And these are different because they aren't fluctuations in energy or matter. They are fluctuations in the metric of space-time itself.
So not ripples in something, but ripples of something. Ripples of the canvas.
That's it exactly. These are the primordial gravitational waves. They are the direct signature of the gravitational field itself undergoing those quantum jitters during inflation. They exist without any matter at all.
And this is where it gets really profound, because detecting these isn't just about inflation.
No. The existence of these tensor modes, it's a direct prediction you get only when you combine general relativity with quantum mechanics. In a purely classical universe, the vacuum is smooth. No jitters, no ripples to stretch.
So finding them.
Finding them is the first empirical proof that gravity must be a quantum field. It's the ultimate connection.
Okay, we'll definitely come back to that, but for now, the detective work.
Yeah.
How on earth do you find these microscopic quantum events that have been stretched to cosmological scales and are now impossibly faint?
You look at the oldest light in the universe. You look at the cosmic microwave background, the CMB.
Our evidence sheet.
It is. It's the light from the surface of last scattering, released about 380,000 years after the Big Bang.
Yeah.
That's when the universe finally cooled down enough for atoms to form.
And light could travel freely for the first time.
Right. Before that, it was an opaque plasma. But at that moment, the photons were set free. And that light, now redshifted by 13.8 billion years of expansion, is what we see today as a faint microwave glow all over the sky.
And we're not looking at its temperature anymore. We're looking at its twist.
Yeah.
This is where we get to the smoking gun. B-mode polarization.
Right. Polarization is just the orientation of the light waves. And as that ancient light scattered off the primordial plasma, it picked up a polarization pattern. We can break that pattern down mathematically into two distinct types.
Like separating a sound into its different frequencies.
A good way to think of it. We decompose the pattern into E modes and B modes.
So let's get these straight. E modes, what do they look like? What makes them?
E modes, or gradient modes, are symmetrical. They have no handedness, no twist. They look like lines radiating out from a point or circles around a point. They're generated by those scalar density perturbations we talked about, the lumps.
So clumps of matter create these straight line patterns.
When photons scatter off them, yes.
Right.
So E modes are the dominant pattern. We expect to see them. They're, for our purposes, the boring part.
Then we get to the prize, the B modes.
The B modes, the curl modes. These are fundamentally different. They have a handedness, a chirality. They look like swirling, twisting vertices on the sky, a true curl.
And this is the whole game, right? The crucial insight.
This is everything. Scalar perturbations cannot generate B modes. The lumps, the density changes, they can't create that twist.
So if you see that swirl, that primordial swirl, it can't be from the normal stuff that makes galaxies.
It can't. There are only two things that can generate a B-mode pattern at these large scales. The first is a kind of noise we have to deal with, gravitational lensing.
The light getting distorted on its way to us.
Exactly. As the CMB light travels for billions of years, it passes by galaxies and clusters, and their gravity acts like a lens, bending the light. This process can take the nice straight E modes and twist them into a B mode pattern.
So that's contamination.
It's foreground noise. We can model it and subtract it. It's a process we call delensing. But the second phenomenon...
The cosmological prize.
The second phenomenon is a primordial gravitational wave from the Big Bang. That stretching and squeezing of space-time as the wave passes through imparts a definitive, characteristic twisting motion to the polarization of the CMB photons.
The graviton fingerprint.
That's what it is. It is the undeniable, holy grail signature of inflation.
And finding it doesn't just tell us inflation happened, it gives us a number, a measurement of how violent it was.
Precisely. The strength of that B-mode signal is measured by a number called the tensor-to-scalar ratio, or just... It's literally just a ratio. It compares the power in the tensor waves, the space-time ripples, to the power in the scalar waves, the density lumps. When you measure dollars, you're directly measuring the strength of the gravitational waves.
And why is that one number so revolutionary for particle physics?
Because the theory of inflation gives us a beautiful direct link between that number, $2, and the energy scale of inflation itself. Basically, a bigger dollar means a higher energy.
And what kind of energy are we talking about here? Something we could build in a lab.
Not a chance. We are talking about the grand unified theory scale, about 10 to the 16 JeV.
For comparison, the Large Hadron Collider.
It's about 10 to the 4 JeV. It's a trillion times less powerful. To build a machine on Earth to reach the energy of inflation, it would need to be the size of the Milky Way galaxy.
So we can't build it.
But we don't have to. We're using the entire observable universe as our particle detector. The value of $3 is the dial on that detector that tells us exactly how high the energy was.
The current limits put $3 at less than 0.036, so it's a very faint signal.
Incredibly faint.
But this hunt, this quest has its own scar tissue. A really dramatic, almost tragic story that completely changed the rules of the game.
It did.
We have to talk about the cautionary tale. The BICFP2 saga, the false dawn of 2014.
It was maybe the single most euphoric day in modern cosmology, immediately followed by the most public, sobering correction you can imagine.
So set the scene. March 2014.
The BICFP2 team, working from an experiment at the South Pole, one of the best places on Earth to do this kind of observation, held a press conference. And they announced they had found it, a massive B-mode signal.
And the announcement was, it was electric, it was everywhere. Definitive proof of inflation. The first tremors of the Big Bang. Nobel Prize practically guaranteed.
They claimed a value around $1.20. That's a huge signal. Enormous. It would have validated the simplest, most elegant models of inflation. And they said the detection was at a confidence level of over 5 sigma.
The gold standard for a discovery.
The gold standard. But the tragedy was what they were actually seeing. They thought they'd seen the face of God. But they were looking at something much, much closer to home.
They were looking at dust.
Galactic dust. The fatal error was foreground contamination. The BICFP2 telescope was amazing, but it operated at a single frequency. 150 gigahertz. And at that frequency, yes, the cosmic microwave background is bright, but so is the dust in our own Milky Way galaxy. These little interstellar grains, they get aligned by the galaxy's magnetic fields, and they emit polarized light that can perfectly mimic a B-mode signal.
The challenge isn't just seeing the twist, it's proving the twist isn't from something else.
And to do that, you have to subtract the foregrounds. But with only one frequency, they couldn't. They needed data from other frequencies to see how the color of the signal changed, to distinguish the CMB from the dust.
And the data they needed was held by another experiment.
By the Planck satellite from the European Space Agency. Planck was mapping the whole sky at many frequencies, but their official calibrated dust maps weren't public yet. So BICFP2 had to estimate the dust on their own.
And this is the part of the story that just sounds unbelievable. The forensic detail. How did they try to estimate the dust?
This is where science becomes a human story. Lacking the official data, they controversially used data scraped from a digitized PDF slide.
A PDF?
A slide from a PowerPoint presentation that a Planck scientist had given at a conference months earlier. It was a preliminary, uncalibrated map. They basically zoomed in on this graphic and tried to estimate the dust levels in their patch of sky from that.
That's astounding.
Yeah.
Basing a Nobel-winning discovery on a screenshot of a conference talk.
It's a painful lesson, but a vital one. They concluded the dust was low. They were wrong.
And when the real maps came out?
When the official calibrated Planck maps were released later that year, the reality was brutal. The clean patch of sky BISF2 had been staring at was actually full of polarized dust loops. The dust was exactly where their signal was strongest.
And the final verdict.
A joint analysis was published in 2015. It confirmed the entire signal seen by BISF2 could be explained by the magnetic ash of our own galaxy. The primordial signal was consistent with zero.
That failure was a hard reset for the entire field.
It established what we now call the multichroic imperative. You cannot do this with one color. You have to observe in multiple frequency bands simultaneously to tell the signals apart. The universe is dirty. It hides its secrets behind a wall of magnetic ash.
Which sets the stage for the theoretical war we're in right now. The fact that we haven't found a signal yet, that the upper limit on $2 is so low it's sharpened the conflict. The search for B modes is now the weapon that will decide the victor.
It really is a high-stakes war between these major cosmological ideas, and they each make a unique prediction for the gravitational wave spectrum, specifically for its tilt.
The tilt. Okay, so let's start with the reigning champion, team inflation. The bang, what is their specific prediction?
Standard simple inflation, the kind everyone hoped BIC2 had found, makes a very specific prediction. It predicts a red tilt.
A red tilt. What does that mean physically?
It means the power of the waves is strongest at large scales, which corresponds to low frequencies. And the power gets weaker and weaker as you go to smaller scales, higher frequencies.
So the lowest notes are the loudest.
Exactly. The low-frequency hum from the beginning of time is the strongest part of the signal. So if we find B modes in the CMB, which is looking at those very large scales, and they have this red tilt, it's a huge confirmation for the standard picture.
And if that picture is confirmed, the implications go way beyond just the Big Bang. It points towards the multiverse.
It does. If we find B modes, it confirms inflation happened at that incredibly high energy scale. And at that energy, our theory strongly suggests that inflation becomes eternal.
Eternal.
It never stops everywhere at once. Quantum fluctuations are so strong they keep kicking it off again in different regions. So our universe is just one bubble that stopped inflating, that cooled down. But outside our bubble, the inflating space keeps going, spawning off an infinite foam of other universes.
So a win for teen inflation is really a vote for the multiverse.
It's the first piece of potential empirical evidence for it. The stakes are that high.
Okay, that's one faction. Now for the radical challenger. The theory that wants to get rid of the beginning altogether. Team loop, quantum cosmology. The bounce.
LQC, yes. This comes from loop quantum gravity, which is an attempt to quantize space-time itself to make it out of little pixels. And when you apply that to the whole universe, the singularity disappears.
No point of infinite density.
It gets replaced by a big bounce. The universe contracts down to a maximum possible density, the Planck density, and then quantum repulsive forces kick in and force it to expand again. It's a breathing organism, not a one-time explosion.
And the bounce makes two very different predictions. What's the first signature?
The first is a predicted suppression of power at the very largest angular scales on the sky, the lowest notes in the cosmic symphony, if you will.
Why would it suppress those?
Because in the bounce picture, those largest scales are bigger than the universe was just before it bounced. So they interacted with the pre-bounce curvature of space-time differently, which leaves a specific signature. A lack of power.
And this is where LQC has a kind of home field advantage.
It does, because the Planck satellite already observed this. We see a statistically significant lack of power at those largest scales. It's called the low quadrupole anomaly.
Which inflation struggles to explain.
Inflation basically has to call it a statistical fluke, cosmic variance. But for LQC, it's a natural prediction. It's their first piece of corroborating evidence.
And what about the gravitational waves themselves, the tilt?
This is where it gets tricky for them. Some LQC models predict a very faint signal, an extremely small tensor to scalar ratio, something like $3 around 10 to the minus 4.
That's 100 times smaller than our current limits.
It's so faint we might never be able to see it in the CMB. If the universe bounced in that way, the B-mode signal could be hidden in the noise forever.
Which brings us to the third faction, the exotic wild card. Team string gas cosmology.
The third way, yes. This comes out of string theory, and it says the universe didn't start as a point or a bounce, but as a hot, dense gas of fundamental strings in thermal equilibrium.
A completely different starting point.
And a completely opposite prediction. String gas cosmology uniquely predicts a strong blue tilt.
The opposite of inflation.
The exact opposite. Remember, red tilt means power is at low frequencies. Blue tilt means the gravitational wave signal gets stronger at higher frequencies. The high notes are the loudest.
The implication there is huge. It means we've all been looking in the wrong place.
That's the devastating possibility. If the blue tilt is correct, then hunting for a faint signal in the low-frequency CMB is a fool's errand. The real signal would be invisible there, but potentially loud and clear for experiments designed to listen for higher-frequency gravitational waves.
So let's talk about the weapons, the machines we are building to settle this war. The next 10 years, 2025 to 2035, this is when the data comes in.
This is it. We have a three-pronged attack, and each prong is a technological marvel designed to test one of these ideas.
Let's start on the ground. The Simons Observatory, the Hunter.
The SO. It's perched high in the Atacama Desert in Chile, over 5,000 meters up. The location is key. It's above most of the Earth's water vapor, which is what absorbs the microwaves we're trying to see. It's the driest non-polar desert in the world.
And the technology's just, it's mind-bending.
It is. We're talking about over 60,000 detectors. Transition edge sensors. These are basically tiny superconducting thermometers cooled to within a hair's breadth of absolute zero, about 100 millikelvin.
Why so cold? Why that specific temperature?
Because at that knife's edge temperature, when a single microwave photon, one photon of the oldest light in the universe hits the detector, it provides just enough heat to push it out of its superconducting state.
And that creates a signal.
A huge, measurable jump in its electrical resistance. We are detecting individual photons of light from the dawn of time.
And the observatory itself is split into two parts, right? The SATs and the LAT.
Yes, this is to avoid the Biaisiki 2 mistake. The small aperture telescopes, or SATs, are the B-mode hunters. They scan big patches of the sky at multiple frequencies, looking for that faint, large-scale twist.
And the big one, the Large Aperture Telescope.
The LAT is the noise canceller. Its job is to map the gravitational lensing B modes, the foreground contamination, with incredibly high resolution.
So it maps the noise.
So that we can then subtract that noise map from the data the SATs are taking. It delenses the sky, hopefully revealing the true primordial signal hidden underneath.
Their target is a sensitivity of about 0.003 for $2. If inflation is real and not absurdly weak, they should see it. But they can't see the whole sky. To test the big bounce, we have to go to space.
The light bird.
This is a Japanese-led mission launching around 2032. It's a satellite going out to the L2 Lagrange point, 1,000,000 miles from Earth.
And its advantage is full sky coverage.
Full sky, and crucially, it can see those absolute largest angular scales, the lowest notes, the part of the sky that ground-based telescopes can't observe well.
Which makes it the perfect machine to test that LQC suppression prediction.
It is the LQC killer, or confirmer. That predicted lack of power from the bounce only shows up at those largest scales. If Lightbird maps the sky and sees that suppression, it's a massive win for the bounce. If it sees full power, as inflation predicts, then that part of the bounce theory is dead. And its target sensitivity is even more insane. Delta R less than 0.001. But what if they both find nothing? If the CMB is clean of any primordial twist, we have to shift our focus completely to the high-frequency sentinel.
To LISA, the Laser Interferometer Space Antenna. This is the ultimate tiebreaker. It's planned for 2035, and it's not a telescope at all.
It's an interferometer. The scale is just galactic.
It's 3 spacecraft flying in a perfect triangle with 2.5 million kilometer arms. They will bounce lasers between them, measuring the distance to an accuracy smaller than an atom, looking for the stretching and squeezing of space-time from a passing gravitational wave.
We know LIGO, which hears black holes merging at hundreds of hertz.
Yeah.
Where does LISA listen?
LISA is listening in the millihertz band, much lower frequency than LIGO, but critically, it is vastly higher frequency than the CMB. There's a huge gap in the spectrum between what the CMB sees and what LISA hears.
And that gap is the blue tilt trap.
It is. Remember, Team Inflation's prediction, a red tilt. The signal gets weaker at high frequencies. So for standard inflation, the signal at LISA's frequency is basically 0. Inflation predicts LISA will hear nothing from the early universe.
But if string gas cosmology is right,
if the blue tilt is correct, the signal gets stronger with frequency. It could be loud enough for LISA to hear a constant stochastic background hum.
So if LISA hears a hum,
standard inflation is dead, falsified. It would be direct evidence for a blue tilt, pointing straight at exotic physics like string gas cosmology. The origin of the universe would be something far stranger than we imagined.
It's just staggering. The most advanced instruments ever conceived, all to measure the tilt of a 13.8 billion-year-old whisper.
And this brings us back to the very beginning, to the graviton. Because the most profound part of finding these B-modes isn't just about inflation. It's about proving that gravity itself must be quantized.
How does finding a big twist in the sky prove something is happening at the quantum level?
Because of how they were made. The only way to generate these primordial gravitational waves is for spacetime itself to have those zero-point vacuum fluctuations. Classical gravity says the vacuum is smooth. Only quantum gravity, where the field is made of particles gravitons, says the vacuum jitters.
The B mode is a quantum signature blown up to the size of the cosmos.
That's precisely it. The math that describes the strength of these waves has Planck's constant in it. If Planck's constant were zero, if we lived in a classical world, there would be no B-mode signal. The CMB acted like a giant amplifier, taking a microscopic quantum event, the creation of virtual gravitons, and freezing it into a pattern across the entire sky. We find the graviton by measuring ripples across billions of light years.
It's like we're developing a new sense. We've mastered sight, looking with light all the way back to the CMB.
We have seen it. And with LEGO, we've started to feel it, those high-frequency chirps from black holes. Now, with these new machines, we're learning to hear it, to hear the ancient, low-frequency hum of the beginning itself.
We're standing at this incredible fork in the road, and the data from this next decade will force us down one of three paths. So let's lay them out one last time.
Scenario 1. The red tilt victory. Simon's observatory finds B-modes with a red tilt. This is the win for the standard model. Inflation is confirmed, gravity is quantized, and we probably live in an eternal multiverse. The Big Bang was real.
Scenario 2. The bounce validation. Simons and Lightbird find nothing. Or, critically, Lightbird sees that suppression of power at the largest scales.
That's the victory for the big bounce. The singularity is gone, replaced by a maximum density. It supports a more holographic, pixelated view of reality, where space-time itself has a fundamental limit. The universe didn't explode, it transitioned.
And finally, Scenario 3. The blue tilt trap. The CMB hunters find nothing, but Lysa, out in deep space, hears a persistent high-frequency hum.
The most radical outcome. Standard inflation is dead. The hum means a blue tilt, pointing to something like string gas cosmology. The universe began in a state of exotic, high-dimensional physics we barely understand.
No matter what happens, the next decade will fossilize one theory and breathe life into another. It will fundamentally rewrite our story of creation. For you listening, what stands out about the possibilities that lay ahead in this ultimate cosmic detective story?